Welcome XNA students to a very special bonus video. This video was originally not going to be in the course, but hey, why not throw a little something special your way? See, from time to time, Logan needs to create, well, temporary throwaway utility apps that he uses to help put together various things he's working on with different projects. Right now, since we're focused on, well, tile sheets, one of the things he needed was an application that would allow him to quickly assemble a series of frames into a single tile sheet. So if we were to go into 3ds Max, Maya, or some other application and you render out a whole bunch of individual frames, which of course if played back rapidly we now have our animated sequence, but he needs all of this to be put into a tile sheet. So he wrote a quick application to do it. And I saw it and was like, hey, that's pretty nice. We should, show the students. And of course Logan's response was, well, this is just a real quick thrown together utility application. It wasn't on the docket to actually be taught, and it's not very clean, very efficient. It just gets the job done. And I thought, hey, perfect. Let's throw it out as a bonus video. Now, there are some things in here that we have not talked about much in the past, like back buffers, etc. And I figure that those of you that are interested can watch this video, and if you, feel so inclined, you can head over to the good old help file and do a little bit of additional researching. But as Logan walks through this application, he'll explain what everything's doing, and I'm sure everybody's going to feel quite comfortable with an understanding of what's taking place. Also, I thought it would be kind of cool to record this to demonstrate what does a very rough utility app look like that's thrown together by a programmer? So, one that doesn't need to spend a lot of time and think about optimization and memory usage, etc., etc. So that is exactly what you guys are going to get to see. So with the application that Logan's going to be writing, of course, it's a very raw application, no user interface or anything like that. Quite simple. It's only going to be looking for just a few pieces of information. We're going to be looking for the overall texture width, the overall texture height, and we're also going to be looking for how many tiles would fit going across in the X direction. That's pretty much everything we need there. Of course, we're going to need to know things like what is our in path, so we know where to go and find all of these different frames at, and in the end, what will be our out file, because we need to save this tile sheet out as some sort of graphic, so we'll save it out as a PNG file. So Logan, is that pretty clear for just a real quick overview of what it is we're about to do?
Right, that's what the goal that this application is going to try to accomplish. And I will stress again that this is a very quick and dirty app. There is no user interface. There is no real error checking. The methods used may not be the cleanest or even most correct, but the only goal of this application is that it run for long enough to generate the desired output. It does not have to run continuously. We're not worried about any type of memory problems or anything.
Exactly. So you guys know what it is that we are out to accomplish. Just take a sequence of files and put those into a single tile sheet. So that is the objective. Kick back and take a look. Logan, let's go and get started.
All right. The very first thing that I want to take a look at is what is the raw data that we're going to need to deal with? What do the actual frames look like?
Okay.
Well, in our working folder, I've assembled 3 different folders: an input 1 folder, an input 2 folder, and an output folder. Inside of input 1, we have the 29 frame sequence that made up the tile sheet that was used in the previous video. So I can open any of these frames, and we see individual frames starting at frame 0, ending at frame 28 to give the full 29 frame sequence. And you'll also note that as I click on these, we get the dimensions as 160 by 120. This will be important to us when we go to come up with the math, the texture width and height for our overall tile sheet.
Okay. Now you have another input folder.
Well, up here we've got input 2. The reason I put this together, I only have 4 images in here. I put these series of images together so that we can look at handling transparency. In the initial implementation that I wrote of this program, it had no support for transparency, which was all right on our last tile sheet because none of the frames were transparent. Even though you can't really see it here in the picture viewer, this image is in fact transparent. Everything that is not black in color is transparent in this image. So we'll use this as a test to first highlight the problem with our first method and then make sure that we prove that our fix is working once we implement transparency. And of course the final folder here is the output folder. This is where the final tile sheet graphic will be assembled and then saved to.
So right now if we jump up in there, we'll see that it is indeed empty.
Absolutely empty.
All right.
So now that we know all of these things and what kind of data we're dealing with, we can jump into Visual Studio and let's take a look at putting this together.
All right.
We'll start a new project. I'm going to build this as a Windows game, so maybe a little bit unorthodox for what you would generally think of as a utility, but that's because I'm going to leverage the frame buffer and set up a render target, and that way I won't have to worry about looking at individual texture data. We may have to look at that for some of the more in-depth things in Spacefighter, but for the time being that allows us to very quickly render a lot of things to the frame buffer, gain access to that data, and then save it. So this is indeed going to be a Windows game. We're going to call this, what do we want to call it? Sprite Sheet Builder. Might be a good name. So Sprite Sheet.
Got a J in there. Sprite Sheet Builder.
Oh, close enough. Yes.
And it's a T.
As soon as I typed that, I saw you looking at the screen. Yep.
The Sprite Sheet
You're all over
that.
Sheet Build.
All right.
So, okay, this should be about the hardest part of the program is the name. Once we get past this, we should be good to go.
Fantastic.
All right, but with our new project, now we can take a look at what it is we need to do. We don't need to worry about any extra classes or textures internal to the project, so we won't worry about anything over here. We'll simply begin with the fields that we're going to need inside of the program itself. I'm going to jump up a few lines above our Graphics Device Manager and Content Manager, and let's drop in some fields that we can use to describe a sprite sheet. We're going to start with a few integers. First integer will be the texture width. Texture width, this is going to be the overall width of the resulting texture, the final sprite sheet. And there's no other place that this is going to be set. This is going to provide the only interface here, and that is going to be the setting of these fields. So that means how wide does the sprite field actually need to be? Since we're setting these in, I'm going to go back to those graphics and figure out what we actually need. As a matter of fact, I'll just leave that an error in question marks for the time being. I want to get to the third field so that I can fully describe all of this.
Okay.
So that means we will momentarily move ahead. We'll put in the texture height field as well, the overall height of the sprite sheet. And then we get to the final one I wanted to use to describe the sprite sheet, and that was the tiles X field. Just as seen in the sprite animation class, tiles X is the number of tiles across the width of the texture. And we're going to set this to 5, because if you remember from the last lesson, we had 5 tiles across by 6 tiles down. So we want to duplicate that tile sheet, so our tiles X value here is 5. Knowing that we have 5 tiles across, we need to find a number that we can plug in to texture width, meaning we know we're going to have 5 tiles, but how wide is each individual tile? Well, if we look over here at the files we're going to be using, we have a width of 160 pixels. So we could very quickly bring up a calculator and plug in 160 pixels times 5 tiles across gives us a value of 800. So our resulting sheet is going to be 800 pixels across. Now we can do the same calculation for the height. Let me pull that image back up and just verify that our height is indeed 120 pixels per tile, and therefore the calculator should tell us that 120 times 6 tiles high would give us a height of 720 pixels, which we can plug in right here. And that is all the information that we need to describe the tile sheet. We will add a few more fields here so that we can, so that the program itself can maintain some data as it's working with the texture and the tile data. One other thing we're going to add is a sprite batch, which is going to be used to not only give ourselves a preview, but also do the actual assembling of the tile sheet. So we're going to drop in a sprite batch field, and we'll stick with the standard naming of sprite batch. And let's see, a few more things that we want to add, including an internal tile width and tile height, which will most likely end up becoming that 160 and 120. It's just something that the program can use to size each individual tile. So we'll drop those in here as int tile width and tile height. After that, we're going to make an array of texture 2D and then a final target texture as a texture 2D. So the first is going to be a texture 2D array called textures. And this will be used to hold references to all of the textures found within that folder. So as we saw in that folder that had 29 images, we're going to create an array with that many elements and store all of the textures in texture 2D references. And of course our final field is going to be the texture 2D called target texture. This is the texture that's going to hold the data of the assembled sprite sheet. So moving into the actual coding phase, the first thing we need to address is the constructor. Since we're using the back buffer to build the tile sheet, we need to make sure that we set our overall preferred back buffer width and height to be equal to these dimensions from the texture width and height. So we need to take our graphics preferred back buffer width and set that to texture width, and set preferred back buffer height to texture height. And looking back a few steps, there is one other thing I wanted to address. Some of these things will be similar to the sprite animation program, meaning fields like tile width, tile height, tiles X, but you'll notice that we don't have a tiles Y field.
Mm-hmm.
Why is that? Well, it turns out we don't even need tiles Y in either of these two engines. Even in the sprite animation class itself, it was not necessary to hold a tiles
That's
Y
right.
field.
We did the modulus tiles X when going across, and then we did divide by tile X to figure out which row we were on. We never used
Exactly. Tiles Y never came into the equation. As a matter of fact, I have that project still loaded in the background. So just to show you what I'm talking about, back in the previous video's class, the sprite class, if we jump over to the sprite class and scroll up to the top, of course, here's where we had that original tiles Y field.
Mm-hmm.
And just to prove that it's unnecessary, I could comment out that field and then scroll down to the constructor where we assign the tiles Y field. Build results in no errors. Running results in no errors. And everything is animating just fine.
Beautiful.
Because, of course, if you remember here in the math, we use tiles X for both the X and Y. There was no need to store a tiles Y.
Right.
So why was it stored in that class? Well, to be honest, it just seemed like a good idea at the time.
Good answer.
And do keep in mind that tiles Y is still necessary in the constructor to the sprite,
Mm-hmm.
both in figuring out things like the texture height. Tiles Y fed in as a parameter is necessary to find that calculation, and is also necessary in the automatic frame count version of the constructor, where we multiply tiles X against tiles Y.
Right.
But it is unnecessary to store it in the individual field.
Exactly.
So just thought I'd point that out real quick. So back over to our sprite sheet builder. We were in the middle of adding texture width and height to the constructor. Again, like I was saying, the back buffer is used to assemble the sprite sheet, and that means our actual screen resolution needs to be set to the texture dimension. And that could potentially limit the sizes that this utility is capable of creating, because that has to be a valid back buffer that your video card can handle. Now, I've tested a few odd sizes, and it seems to be working just fine for any of the sprite sheets I've needed to make. But just keep that in mind that if it explodes, you may need to find an alternate method, or just resize the tile sheet that would be accepted. But just pointing that out so you can keep that in mind. All right, moving on to initialize. Here we're going to simply create the sprite batch. So back into the world of some standard concepts for a moment. We'll drop in a sprite batch is equal to new sprite batch using the graphics.graphics device. Alright, moving on from the initialize method. Now we get into some of the fun stuff. Let's go down to load graphics content, and we'll take a look at loading in all of those individual frames, all of those individual files, and assembling our target texture. So to begin with, let me first create the target texture instance itself. And this is going to be a different look at making a texture 2D. Up until this point, all of our texture 2Ds have come from the content manager. We've used it to load assets into texture 2D instances. Mm-hmm. Here we need to make a new texture 2D from scratch so that we have an empty texture into which we can render our sprite sheet data. So we'll take our texture... Where's a target texture? Target texture is going to be equal to a new instance of texture 2D, and then we need to satisfy all the parameters to the texture 2D's constructor, beginning with the graphics device itself. So just like in the case of the sprite batch, we can feed in graphics.graphics device. We need to specify a width and a height for this new texture, and that comes from above where we have texture width and texture height. After that, we have a parameter called number of levels, and as the tooltip itself would also explain, number of levels deals with mip-mapping, smaller versions, scaled-down versions of the texture stored in the same actual memory, in the same, I guess you could say, virtual file, if you will. In our case, mip-mapping is irrelevant to how we're going to use this texture. It's not going to be scaled or rendered in 3D. The data is simply going to be saved back out. So I'm going to set the number of levels to 1. We don't need to worry about mip-mapping levels. The resource usage here, if we drop down resource usage and look at all of the flags available, we have quite a few different ones, which not many I'm going to get into, but I do want to point out that we're going to use resolve target, because we're going to resolve the rendered back buffer to some other location, so we need to set this texture up as a resolve target. And let's see, next we need to look at the surface format. How is data stored within this texture 2D? I'm going to use a surface format of surfaceFormat.color, so that way we work in the same familiar color space as the color type itself. And finally, we need to address the resource management mode, because in the case of the render target, we can't leave this as resource management mode automatic. We have to change this over to resource management mode.manual because of the way it's going to handle the back buffer. And with that excessively long line is now put together. We'll have a new texture created, no usable data in it yet, but it is a place where we can store data out of the back buffer. Alright, so our next task is to open up that directory that has all the PNG frames in it, and then scan through it and load each file out into a file info array.
So with that, let's go ahead and jump back up and add in the in-path and out-path.
Oh, I completely skipped over those.
That's all good. I was prepared.
There's one other thing we have to add. So first thing, let's add in 2 fields to let us show where our input and output paths are. So we'll start with the first, which is going to be called in-path. And we'll go ahead and set that right here to a value of C drive, our working folder, and then input.
And input. There you go.
Alright, that takes care of in-path. We're also going to have a field called outfile. And this will be the sprite sheet 2 output. And it will have a value of C drive, our working folder, output folder, and then we'll give this an actual file name. This will be tile_sheet.png. So that will be the file to write to after we make our file. Now, one other thing I want to point out is we're about to get into some file I/O. We need to get access to things like the directory info and the file info. Those things are found within the system.io namespace. So if I expand our using statements, we can add in a using for system.io. And now if we move back down to load graphics content, we can turn around and start using some of that stuff. The first thing we need is a directory info variable. So here we have directory info. I'll simply call this variable directory, and then turn around and instantiate a new instance of directory info where we'll feed it a path. Now, of course, we already have the field as in path, so we'll feed that over to our directory info, and that will create a new instance. Once we have our instance of directory info, we need to check that instance and see if it exists, which can be done very simply by looking at our instance. That is directory info, or excuse me, just directory dot exists. This will be a Boolean property that tells us whether or not this directory does in fact exist. Because if it does, we want to scan through and get all of the files out of that directory and store them in a file info array. So I'll declare a file info array variable, which I will call files, and set that to be a a call to directory. One of the methods of our directory info is a getFiles method. GetFiles returns a type of file info array. So we'll get files and close off the call, and that will get all of the files from the directory, which does mean
syncs up.
And that does mean we need to be careful because I'm not putting any filter into get files. That means any file will be attempted to be loaded. So if you have a zip file or an executable file in that folder, then it'll probably cause a lot of problems when it tries to read that data.
Again, just a down and dirty utility that you were using, and you knew exactly how you were going to be using it. You wasn't trying to package this up for a group of users or to be released to the mass public or anything like that.
Exactly. I was going to go 5 minutes after I'm done writing it, go and put the files in the folder so I know what I've just written, I'll know how to handle that. All right, now that we have a list of all of the files within that directory, we can create our textures array, since the first thing we know about that files array is how many files are in it. So that means we can say, or go ahead and look at our textures array and create it. So we want a new array of texture2D with the number of elements matching the number of elements in the files array, or files.length. All right, now that we've got texture set up, a place to load texture data into, we can loop through each of those individual frames and load the data into our textures array. So we'll set up a for loop to loop for all of files.length, and then for every file that we find, we want to instantiate each element in the textures array. So we can look at textures sub I and set that equal to a texture2D. If we look at the texture2D type itself, we have a from file method. And this will allow us to load data in from the PNG files as opposed to relying on the content management system. So if we say texture2D.fromFile, this needs to have access to the graphics device. So we'll feed in graphics.graphicsDevice. And then if we look at one of the, I believe it's the next overload, second overload, we can feed in a file name as a string. And we have that file name as the current file that we're looking at within the files array. So that would be files sub I.fullname. And that will give us the current PNG file that we're looking at. So we'll feed that over, get that loaded into the textures array, and that pretty much covers the loop. Once we have all of our texture data loaded, now we can initialize the two remaining fields, the tile width and tile height fields. And I'm going to set these equal to the, we'll just look at the first texture element, texture sub0.width and height. Now this of course means the code will not gracefully handle tiles that differ in size as you're looking at them, but again, very simple utility with a very strict set of requirements. All of the tile textures must be the same size. And therefore we can just look at a single one instead of worrying about averaging or individual widths and heights. Alright. So that takes care of loading in the texture data into a textures array. Now after here I want to call a method that is going to build the texture itself, assemble all of these textures into a full tile sheet and save that back out. But we need to write, or at the very least, skeleton that method before we make the call to it. So let me just jot down a note here. To do call build routine. Or build method, which is what we'll address right here. I'm going to scroll all the way down to right below our draw method, and I'm going to drop in
right below or right after.
Right after. Yes, same thing, right?
Right. Oh, you said right before.
Oh yes, right after.
Yeah.
Right. I see.
It just kind of threw me off for a second. Right before, as I start typing it, right after.
All right. But any other way would work, of course. But
yes,
in the general area of the bottom of the class, we're going to put in a private method that's going to be called build texture. Its job is to assemble all of the tiles and then save the texture data. So this is going to be private void build texture. I guess more accurately it could be build tile sheet or what have you, but it's the only custom method in the app, so we'll just leave it be. And before I go too far ahead and forget, I'm going to jump back up to the load graphics content method and put in our call to build texture. All right, now on to the build texture method itself. The idea here within build texture is I'm actually going to set up the sprite batch and have the sprite batch draw the tile sheet. Then I'm going to turn around and look at the back buffer data resulting from those draw calls and save it to a file. So that means we're going to need to treat this build texture method very much like a call to draw, beginning with the telling the graphics device to clear the back buffer in case there's any garbage still left over from some previous run. So we'll look at graphics, look at the graphics device, tell it to clear the back buffer, and put in the color. We'll put in the default cornflower blue, because just like I had done in the sprite sheet from the sprite sheet class example, that means if there's tiles that don't contain an actual image, they're bright blue and obviously easy to tell. So we have some known color that is supposed to be there.
Okay.
And then after we clear the back buffer, we'll use the sprite batch to assemble our tile sheet. So we'll tell the sprite batch to begin. Jump down a few lines just so we remember to put in our call to sprite batch.end. And now we need to loop through all of the textures that we have in our textures array and arrange them in a tile sheet. So we'll use a for loop to iterate through all of the textures, using textures as the length for the target that we're going, or for the number of textures that we're looking for. And now we're going to use the same math that we used in the tile sheet application itself. As here we need to find positional information to drop tiles at. Same as if we were looking for tiles to read back. So we're going to make two integers, integer x and y. Integer x is going to be equal to the current value, I, modulus the number of tiles in x, and multiply that value by the individual tile width. So exact same formula as the sprite class. I'll copy and paste that line because there's plenty of similarities in it, changing the variable name to y, making sure that we change the division to integer division, so I divided by tiles x, and now looking for the height of individual tiles, or the variable, or excuse me, the field tile height. So this will get the proper coordinates for the current tile. Now we can make a call to spritebatch.draw and use the information we've gathered. The current texture for this place in the tile sheet will be textures sub I. The position we'll describe as a new vector2, where we'll feed in x and y. And the color will be white, so we're not doing any color modulation with this call to draw. And with that, that will have all of the tiles placed into a tile sheet on the back buffer. Now we need to take a look at getting that data back out of the back buffer and putting it somewhere useful, like a texture reference. So after the call to spritebatch.end, and we want to make sure that we do in fact call spritebatch.end, so any sprites still pending to draw get flushed out and rendered to the back buffer. So make sure we drop down after the spritebatch.end call. Now what we're going to do is grab the graphics device and tell it to resolve the back buffer into our target texture. So let's look at graphics and get the graphics device, tell it to resolve back buffer, or rather, oh yeah, that's right.
Yeah, that's right.
I had seen render target, and we were working with render target a second ago. We want to resolve the back buffer. Resolve back buffer is going to take in a texture 2D as the resolve target, and that will be our target texture. So finish off the call there, and that will have the texture placed in this instance of texture 2D. Now, if you remember, we had the ability to load texture 2D data out of files using the from file. We can also save texture 2D data back to a file. If we look at the instance in question, in this case, target texture, look at its methods, we have a save method. Save can take in a file name and what format we want to save to. We have the file name, complete with full path, stored in out file. And the format that we would like would be PNG. So let's look at the file format options available in image file format. And several down we have the PNG format. So that should work quite nicely in getting the data saved out to the hard drive. And I believe before we even have the engine set up to do a preview render, we should be able to simply run and then check that output folder. Let me build and make sure that there's no errors. Do a quick run where we see nothing out of the ordinary other than the fact that the overall game window is taller than usual. But that makes sense since we had set a preferred back buffer height of 720. Let's close the app down and go to our working folder, jump back up and go to output, and here we have nothing. It's been just a minute and look at this. We've got our call to save. Let me make sure that the call to build is getting called from build texture. Ooh, this is interesting. Does directory exist? I'm going to set a breakpoint and just do some quick debugging here to make sure that if directory does not exist, where were we looking? C, CS input, I had set the folder. The directory does not, in fact, exist.
Yeah.
So the little bit of error checking probably just saved from an exception, though the exception itself would have helped me find the problem faster, as odd as that may be. Our in path was CCS input, but the folders were divided into input 1 and 2, so input simply doesn't exist. So the error was quite accurate. Now if we run, close the application, look at output, there's a tilesheet PNG file.
Very nice.
Let's load that in the image viewer, and there we go. There was the familiar tilesheet that we had used in the sprite sheet example. So everything is working really well. And last time when I was using this for myself in a development environment, this is where I called it. But as I was thinking about the application, I was wondering about transparency, because I had not yet tested transparent sprites in use with this app, and transparent sprites would be very helpful, if not necessary, in many gaming situations.
Sure.
So I wanted to make sure that the application would work on transparent sprites. And if you remember, input 2 has a bunch of, 4 small squares that are transparent. So let's take a look at what the engine does, or what this little utility does with a transparent sprite. I'm going to change the input path to input 2. We'll change the texture width and height. Now, if we look back at these files, just to show this, the dimensions are 64 by 64, and there are 4 of them. So that means the overall texture will be 128 pixels wide, 128 pixels high, and there will be 2 tiles in X. So again, looking at the folder input 2, we'll run, and we see, we never put the render, or the preview render. I'll get to that'll be a good place to put in the preview when we do transparency. But to show what we got here, if we look at our output folder, we have these tiles, and you can see that they were in fact transparent in that they got overlaid over the back buffer color. But that would be an undesirable result if we wanted the tile sheet to maintain transparency,
right,
and have usable transparency in it. So let's take a look at what we might need to do to fix this. If we scroll down to our build texture method, we're clearing to the color cornflower blue. In cornflower blue's alpha, if we look at the tooltip at the very end, alpha is set to 255, or completely opaque.
Right.
We have the option of specifying a transparent alpha for a color. So if we instead made a new color, and we could feed in a color of black with a transparent alpha. So 000 for RGB, we'll specify 4 bytes so we get access to the alpha byte, and specify 0 as well, so completely transparent.
So a much better background.
So now if we run, our output folder has transparency.
Very nice.
Though that can't be absolutely proven inside of this picture viewer, so I'm going to go ahead and code in a preview mode for the game itself. Since we have this usable target texture, there's no reason we couldn't turn around and render that to the screen in the actual calls to draw. So we'll wrap up this little utility by having it preview the sprite sheet that it just generated. So let's see. I'll get into I'll deal with the transparency in just a second. First, let's just draw the texture out to the screen. So let's look at our sprite batch and tell it to begin. We'll make a call to spritebatch.draw and look at the target texture so that we can render it out to the screen. I'll give a position of vector2.0 so that we draw this at the top left corner of the screen, and a color value of white so we have, of course, no modulation. Then we'll put in our call to spritebatch.end, and if we run, now we see everything drawn to the correct background color, though there's still necessarily no indication of the fact that this is transparent since we don't have a patterned texture behind that. So what I'm going to do to indicate and prove without a shadow of a doubt that this is transparent is I'm going to change the color that is cleared behind the back buffer. I'm going to drive it with a sine wave over time so we can watch the color shift back and forth between green and black.
Okay.
And that gives us kind of an animated effect. So what I'm going to do is I'm going to make a byte called G. We'll make this byte stand for green. And then before I forget, I'll turn around and plug that into the call to graphics device.clear. Inside of which we'll make a new color. We'll set 0 for red, the value in G for green, and 0 for blue. So now we need to look at this byte G and store a usable color value in it. Now I'm going to do this all in one line, so this line might get a little bit long, but it begins with doing math.sign on the overall game time. So this will be equal to math.sign And then the value we'll be looking at here is gametime.total gametime.total seconds. Now the result of sine is going to go negative, so I want to make sure I run all of this through math.absolute so that we go from 1 to 0 and then back to 1 again. And then the result of this, let me put, what was it? I guess I wanted a terminator. But all of this is going to return in decimal, and we need to store this in a byte. So we'll cast this entire expression to byte, and like so. Now, of course, we're still dealing with a range of 0 to 1, and byte would be much more useful if it was in a range of 0 to 255. So we could take the final result here, multiply it by 255 before we cast. And now we can add in our terminator. And just since this is a somewhat complicated line, I'll build, make sure that there's no errors in it, and that is looking good. Now if we run, we have a nice animated green texture. So as it drops to black, it looks like nothing's there. So if we would just use black as a preview, it would look broken. But we can see by the background changing now that we have in fact created a transparent sprite sheet. And that finishes the goal that this app needs to do. It makes a sprite sheet out of individual frames. And we've also taken a look at transparency to make sure that that is handled as well.
Exactly. Now, once again, just a reminder, this is a bonus video for the XNA class. This is really just shot without any preparing. You guys get to see exactly what Logan put together as just a very quick, very little thought type application that performs a very specific function. I mean, if you wanted to take this and go a little bit more hardcore, be a little bit more serious about it, you could put in a user interface. So that you could specify things like what is our texture width going to be, our texture height going to be. We could get information in regards to where the texture is going to be located, where do you want to save them out. I mean, there's a lot that you can add in here. Then, of course, things like error checking when you go to read in all the files that are in a folder, make sure that they are of a valid format, etc. Logan's not trapping anything in here. He's not catching any exceptions whatsoever. He's just running it straight as. Like I said, it is a utility that performs a very specific operation, and it follows or needs you to follow a very specific set of rules in order for it to work right. And he's fine with that. There's people that make utilities like this every single day just to help speed them up while they are doing a particular task.
But it is very interesting because we get to use the same algorithm in the animation system itself.
Yeah.
We can leverage that to make the sprite sheets in the first place.
Exactly. So there you guys go. I hope you enjoy it. Hope maybe you got a thing or two out of it. And with that will wrap up this video. Thanks a lot.